Hello students, welcome to the fourth lecture on the design of drop spillway. In this series, this is our fourth lecture and I will be discussing the part 1 of this design. So, the main purpose of this lecture is to evaluate the horizontal pressure forces acting on the drop spillway. You know that for evaluating the stability of any structure, we need to estimate what are the different pressure forces acting on this drop structure. So, here we will be estimating the different horizontal pressure forces, which may be because of the static water pressure, the lateral pressures due to dry and moist backfill materials, and the tail water pressure. You can see this figure, the tail water pressure. If there is tail water, then some negative pressure is created, which is opposite in direction as compared to that of the static water pressure at the upstream side, and lateral pressures due to dry and moist backfill materials. So, before that we should know what are the different functions of different structural parts of this drop structure. So, we have head wall extension, it mostly permit stable soil fill, it prevents the piping around the structure. So, the piping failure is avoided by this. The side wall holds a stable soil fill, protects against erosion due to water passing over the spillway. The wing wall holds a stable soil fill and also prevents the serious scour of the soil fill and gully banks. Similarly, the cut-off wall prevents the piping under the structure. Generally, the piping occurs because of water pressure in the upstream side here. It exerts water pressure, and because of that the water is emitted through this contact surface of this cut-off wall and toe wall to arise at the downstream section like this. So, if the cut-off wall depth is more, then generally the piping failure is avoided. Then it reduces the uplift pressure, it resists sliding, prevents the piping around the structure, and the toe wall also prevents piping around the structure and prevent undermining of apron. The horizontal pressure forces generally depend on the characteristic of backfill material against the wall, soil permeability, cohesion, angle of internal friction, dry weight, moist weight, submerged weight, void ratio and moisture content. Then relative permeability of foundation material and backfill material, elevation of water table and the backfill drainage. Based on the past experience for safe design, generally the total drop is considered as less than equal to 4.5 centimeter, but in general cases we allow maximum 3 meter, and F plus H should be less than equal to 6 meter. So, before estimating the different horizontal pressure forces, we should know what are the different conditions of backfill. So, generally we consider 3 cases of backfill as shown in this figure. The case A shows that there is no backfill against head wall. So, that means there is no backfill and the depth y 0 as shown in this figure is equal to the water depth, which is below the crest level. And the middle figure shows the case B, which is for gully graded fill to crest elevation. So, that means the gully is graded up to the crest elevation So, in this case you have to estimate, or we have to know first what is the line of saturation. You can see this, the line of saturation is at a depth of y 1 from the crest, and after knowing this y 1 you can estimate what is the value of y 2, that equal to here y naught minus y 1. So, that equal to y 2. So, this is the case B condition, and case C condition is for compacted earth field constructed to crest elevation. You can see here there is, in this case there is a tailwater. The tailwater depth is given as T plus S, and the saturation line is shown here. This is the saturation line, and where it is touching the head wall. So, that is my depth y 1, and below the saturation line the depth below to the bottom of this foundation is y 2, such that y 1 plus y 2 equal to y naught, and h is my depth of wear. So, for designing, for estimating the horizontal pressure forces, you have to know these values, that is y 1, y 2, y naught, T and S. So, once these values are known, we can estimate what are my pressure forces. So, we should remember these three cases, what is case A, what is case B, and what is case C. Now, coming to the effect of water table elevation. The elevation of the water table above and below the spillway before and after construction has a significant effect on loads on the head wall and other elements of the design. If the water table is low and the foundation material is relatively homogeneous and permeable, the flow of water from a reservoir or from percolation through backfill in the channel above the dam tends to pass towards through the foundation in vertical direction until it merges with the subsurface flow. And if the water table is high, which is close to or above proposed apron elevation, so in this case a differential head created by the dam of water will result in uplift pressure on the base of the spillway and increased pressure on the head wall. Then the magnitude of this uplift and increased head wall pressure depends upon various conditions like the total differential head, type and efficiency of drainage provided above the head wall, relative permeability of the backfill above the head wall and various strata in the foundation, depth of cutoff and toe walls, physical characteristics of backfill and foundation soils, and tailwater elevation with uplift, and in this case there is a possibility of piping. So, for that we have to provide different drainages. You can see from this figure there are different drainages are provided, and basically these are of two types, one is type small a and type small b, and type small b is mostly recommended to ensure stability against sliding and piping failure. So, here you can see in case of type A, this is a graded gravel filter and the outlet is given here, and this is your backfill material which is compacted earth fill here, and in case of type B the outlet is given here and there is bitumen, sand and gravel filter are shown in this case. So, in most of the cases type B is recommended. So, for designing you have to know this table. So, there are three cases as we have discussed, for backfill condition case A, backfill condition case B and backfill condition case C, and the water table condition can be high or low as we have discussed. Then third column shows the relative permeability of the foundation material to backfill. Then next column shows the drainage type. So, type small a or type small b, generally we have already discussed that type small b is mostly recommended, and the elevation of the saturation line, that is y 2. You can see from this figure y 2 is the elevation below the saturation line, and that can be estimated under no flow condition and under full flow condition. Under no flow condition, y 2 equal to y naught for case A, and for full flow condition also y 2 equal to y naught. And for high water table, and depending on different type of foundation, relative permeability of foundation to backfill, you can estimate what is the value of y 2 from this figure, and here S is the depth of end seal and F is the total fall, and this T, S and F values are given, and accordingly you can see whether there is piping problem or not. If it is yes, then there is piping failure, piping problem, and if there is no, there is no piping problem. So, depending on that condition, you can select what is the value of y 2, your design value of y 2. So, by selecting y 2, suppose I have highlighted here the red one for equal permeability condition and type A drainage, no flow condition. So, y 2 will be S plus 0.5 F, and for full flow condition y 2 will be equal to T plus S plus 0.5 F, and in this case there is a piping problem. And in case of full flow, in case of C condition of backfill, so you may get tail water. So, here the T plus S is the depth of tail water. By knowing all these things from the table, so you can estimate what is your horizontal pressure forces. So, that means you have to know this table. Without this table, you cannot design or you cannot estimate the horizontal pressure forces. Now, everything will be clear if you will solve a problem. This is a typical problem. A drop spillway is to be constructed with the following details. Total fall is given as 2.5 meter, height of end seal S equal to 0.3 meter, depth of flow above crest, that equal capital H, is given as 0.75 meter, tail water height small t, that equal to 0.75 meter, relative permeability for foundation equal to backfill. So, that means you have to use the equal condition as we have seen in the previous table. Water table is high and backfill case is C, that is compacted earth fill bomb constructed to crest elevation. So, all these values has to be used in the previous table as I have shown to find out what is the value of y 2, and by considering the y 2 value as shown in this figure, you can go for estimating the value of y 1, y naught and T plus S, that is your total tail water height above the apron. Then I can estimate what is my pressure forces. Okay. And what else we need? So, for this, the given values of backfill properties are: for dry weight for earth is 1600 kg per meter cube, bitumen sand and gravel 1900, that is mostly used for drainage type B. Moist weight is 1750 for earth, for bitumen sand and gravel it is 2000. Angle of internal friction 25 degree for earth, bitumen sand and gravel it is 35 degree. Submerged weight for earth is 1000 and for bitumen sand and gravel it is 1050. And one, you should know that this is the formula, that is ratio of lateral earth pressure to vertical pressure equal to 1 minus sin phi divided by 1 plus sin phi, where phi is the angle of internal friction. So, here vertical pressure is nothing but that is the total weight of the earth. So, weight can be computed by using the density of dry weight or moist weight, then phi is known. So, by using that you can estimate what is the value of the lateral earth pressure. So, the question is that find the equivalent fluid pressure of the triangle load diagram for no flow type A drainage, no flow type B drainage and with flow type A drainage. So, in this figure you can see this is a type, first one is a type A drainage and second one is a type B drainage, in which case you have to use Petrunchen and gravel filter. So, once these are clear, so now you can go for designing. So, this figure shows a triangle load diagram. The pressure forces are generally estimated as pressure that equal to gamma, pressure is estimated gamma into h, you know this. H is your height of any soil fill or water, gamma is the specific weight. Then you have to estimate what is the pressure diagram in this, the pressure triangle, what is the area of this pressure triangle. Then you can estimate what is the total force from this. So, here you can see that there are different forces acting on this F1, F2, F3, F4, and the question was that you have to estimate the total lateral pressure forces in terms of equivalent fluid pressure. So, this is the main criteria. You have to understand this problem very attentively. So, for no flow and type A drainage, for the backfill case C and type A drainage, consider the backfill as earth for the total height of head wall. So, in this case you have to follow the table, whatever table I have shown. So, this table I have given, I have cut a portion of that. So, here I have to design for equal permeability condition, drainage type small a, and in this case for no flow condition I am getting y 2 equal to s plus 0.5 f, and this is for full flow condition. So, I have to use the value of y 2 that equal to s plus 0.5 f. So, here s equal to y 2 equal to s plus 0.5 f is computed, f is known as 2.5, s equal to 0.3. So, I can estimate it as 1.55 meter. So, height of head wall, from this figure you can see the height of head wall is given as y naught that equal to a plus s. So, that equal to 2.5 plus 0.3 that equal to 2.8 meter. So, once y 2 is known, y naught is known. So, I can estimate what is the value of y 1. So, that is 1.25 meter, and this F 1 diagram shows the moist soil pressure and the diagram F 2 shows the active earth pressure, that is P A. The submerged soil lateral pressure is given by P A 1, which is given by this triangle, which is in yellow color. Then this blue color F 4 is given as lateral water pressure, that is P A 2, which is acting below this saturation line, and this triangle which is a brown color. So, this shows the equivalent fluid pressure, and this x x is my reference line. So, I have to take the moment of all these forces along this x x line to estimate what is my equivalent fluid pressure corresponding to different pressure forces of F 1, F 2, F 3 and F 4. So, this is my basic concept. If you can understand this basic concept, then you can go for estimating the lateral pressure forces. Now, you have to estimate what are the pressure acting below these pressure triangles. For F 1, you can see the pressure is acting as P A, this value is P A. So, this is moist soil pressure. So, moist soil pressure will be gamma into this height, the weight of moist soil into H. So, H is your equal to y 1, that equal to 1.25. So, gamma into y 1. So, that will be equal to your moist soil pressure. So, that can be equal to P A. Similarly, we can estimate for active earth pressure. by using the previous equation W into 1 minus sin phi divided by 1 plus sin phi. Then you can estimate the pressure at the bottom of these different pressure triangles. Then you can multiply with area to estimate the total pressure, area of this triangle. Then you can take the moment about the x line. So, these steps I will discuss in the next slides. So, P A is estimated as 1 minus sin phi divided by 1 plus sin phi into W. W is your vertical pressure, that is nothing but your weight. So, here phi is 25 degree. So, I can get P A equal to 0.406 W. The W is the weight of metal per unit area in kg per meter square. At crest elevation, there is no pressure at crest elevation. So, P A will be equal to 0 at 1.25 meter below crest. So, at along the saturation line, you can see along the saturation line you have to estimate the value of W. So, W equal to, that is the weight of the pressure due to the moist weight of earth. So, gamma into y 1, here gamma is given as 1750 in the question it is given, and y 1 equal to 1.25 meter. So, you can get 2187.5 kg per meter square, and that is equal to 2.1875 ton per meter square. The lateral pressure due to moist backfill can be estimated as, because this is your vertical pressure or vertical weight, that is W here. Now, you can use that equation to estimate what is the value of P A, that is equal to 0.406 W. So, you can get 0.888 ton per meter square. Now, at 2.8 meter below crest. So, 2.8 meter below crest means it is along the x line at the bottom. The lateral pressure due to submerged weight of soil is given by 0.406 gamma into y 2. So, that equal to 0.406 into 1000, that is your submerged weight which is given in the question, and y 2 equal to 1.55 meter. So, you will get 0.629 ton per meter square. So, that is equal to P A 1 as shown here. Then lateral pressure due to water, that is equal to P A 2. So, that is defined by the force F O. So, P A 2 will be equal to gamma W into the height of water, that is equal to y 2. So, gamma W equal to 1000 into 1.55. So, we are getting 1.55 ton per meter square. So, once this is known, now you have to calculate the areas of different pressure triangles. The area of F 1, you can estimate, that is base as P A as seen in the figure, and height is here y 1. So, this area will be equal to half into P A into y 1. Similarly, for F 2, it is a rectangle. So, you will get P A into y 2. So, this height is y 2. So, P A into y 2. Similarly, for F 3, the base is P A 1, that equal to 0.629, and height is y 2. So, this height is y 2. So, it will be half into P A 1 into y 2. Similarly, for F 4, the base is P A 2. So, that is 1.55 ton per meter square you have estimated, and the height is also y 2. So, once this area are known, so you can estimate what are the pressure forces. Now, you have to estimate what are the center of gravities for all these pressure forces, that is F 1, F 2, F 3 and F 4. The center of gravity for F 1, F 2, F 3 and F 4 from the bottom surface are given by these values. So, for f 1 it is y 2 plus y 1 divided by 3, it is acting here. Then for f 2 it is y 2 divided by 2, for f 3 y 2 by 3, and for f 4 it is y 2 divided by 3. So, now we have to take the moment over the reference axis x x. So, the moment for this equivalent fluid pressure, and here the base is gamma equivalent into y 0 into height is equal to y naught, that equal to y 1 plus y 2. So, this area also you can estimate. So, this is your equivalent force which is acting at a distance h by 3 from this base at the center of gravity. Now, you can take the momentum of this triangle, and that is should be equated to the sum of the moments of all these pressure forces or triangles. So, that you can estimate it, that you can estimate by using this equation. So, the first one shows the moment of the equivalent fluid pressure, the second one is the moment of the force F 1, this term shows the moment of force F 2, this one shows the moment of force F 3, and this shows the moment of force F 4 from the x x line. So, once this is known, you can put all these values are already calculated. So, you can get by solving this, you can get the value of q gamma equivalent equal to 0.828 ton per meter cube. So, this solves the first part of the problem. So, once this is solved, now I will go a little speedily for other conditions. So, once this is understood, the same procedure must be followed for solving the next bit of the problem. For no flow type B drainage, so let us assume that the backfill is bitumen, sand and gravel for this phi equal 35 degree, and this is filled up to the height of the head wall. So, in this case P A can be estimated as W into 1 minus sin 35 degree divided by 1 plus sin 35 degree, that equal to 0.271 W, and from the table you can get y 2 equal to S plus 0.15 F from the drainage table that I have already shown. So, here y 2 equal to 0.675 meter and y 1 will be equal to y naught minus y 2. So, that equal to 2.125 meter, and here you can see there are similar forces are acting because it is a no flow type F 1, F 2, F 3, F 4, and the equivalent fluid pressure are shown in the diagram. So, you can follow the same procedure as done in the first bit of this problem. So, at crest level P A equal to 0 at 2.125 meter, you can estimate P A that equal to 0.271 gamma y 1. So, that will give you 1.1518 ton per meter square. Then at the crest level P A equal to 0 and at 2.125 meter, you can calculate P A equal to 1.1518 ton. So, this value, and at 2.8 below crest level you will get P A 1 equal to 0.1921, this value, and P A 2 will be equal to gamma W y 2. So, that equal to 0.67 ton per meter square. So, this value, and after getting these values you have to repeat the steps as we have done in the previous bit. Now, for the third problem we have to use the type A drainage. For type A drainage, here y 2 is computed as T plus S plus 0.5 F from this table. You can see from this table this value I have taken for flow condition, and y 1 equal to y 0 minus y 2, that equal to 0.5 meter. So, you can estimate y 1 equal to 0.5 meter. Here additional force will be the F 6. F 6 is nothing but this is the negative pressure which is acting backwardly because of this tail water. Now, at the crest level, so there is standing water. So, H equal to 0.75 meter. So, you will be getting some water pressure here and P A will be equal to 0.406 into 1000 into 0.75. So, that will equal to 0.3045 ton per meter square. At 0.5 meter, that is below crest level, you will be getting P equal to 0.406 gamma y 1. So, that equal to 0.3553. So, this is equal to 0.3045. At 2.8 meter below crest level, you will be getting P A 1 equal to 0.406 gamma y 2. So, that equal to 0.9338 ton per meter square, and P A 2 will be gamma w into y 2. So, that will equal to 2.3 ton per meter square, this value, and tail water pressure will be equal to gamma w into T plus S, because T plus S is the depth of tail water. Here T plus S equal to 1.5, which is nothing but the F 6 for F 6. So, you will get 1.05 ton per meter square. So, this is my 1.05 ton per meter square. Now, by similar way, now you can use the moment matching technique about the line x x. So, the total moment due to the equivalent fluid pressure, that is given by gamma E q into y naught q divided by 6. So, after summing the total moment, you can see here the negative pressure because of tail water is given by F 6. So, that is half into 1.05 into 1.05 into 1.05 divided by 3, and this value is the distance of the center of gravity from the bottom of the foundation or that x x axis. So, you can get this value is f 1, this is f 2, this is the distance of center of gravity from the x x axis, and similarly this is the distance of the center of gravity from the x x axis. This is f 3, this is f 4, this is f 5, and this is f 6, which is negative. So, by equating that one, you will get gamma equivalent equal to 13.7470 kg per meter square. So, the same procedure is followed as I have told you in the previous bits. In the first bit, you can do this exercise, then more clarity will be there. Unless you want to solve this one, it will be very difficult to understand this, because slightly difficulty is there here in calculating the area of the pressure forces, the area of pressure forces. Then you have to calculate total force equal to pressure into the area of the pressure triangle. Then you have to estimate what is the center of gravity, the distance of the center of gravity from this bottom surface, that is your x x line. Then force into the distance, that is your moment, and you have to equate the moments for equivalent fluid pressure and the other pressure forces. Then you will get what is your equivalent pressure corresponding to different lateral pressure forces. So, this ends the lecture here. So, you have to little practice the problems, then only you can understand all the details, otherwise it is very difficult to cover each and every bit of this pressure calculations. So, you have to in detail I have already told in first bit, and you use those first bit solution to solve the second bit and third bit of this problem. So, this ends our lecture here. Thank you.